Hello, it's Dr. Daystorms again, and in the second part of Chapter 8, we're going to do an introduction to covalent bonds, and I'm going to introduce you to a concept that is so important, I can't stress enough, and that's called electronegativity, because what you'll see throughout chemistry, and especially in organic chemistry and biochemistry, electronegativity explains the reactivity and the different types of reactions that you'll see for years to come throughout your tenure here at Southeastern. So let's get started with covalent bonds. We've already done ionic bonding, and that's where one atom, a metal, gives up an electron or electrons to a nonmetal in order to go so that a cation and the anion can come together and the opposites attract kind of thing, and they form these ionic bonds. Well, covalent bonding, what happens is the two atoms actually share their outer electrons. Okay? And so there's a number of things actually going on right here. So what you're going to see is that we do have electrostatic interaction. Like there's still, the nuclei for each of these atoms are positively charged due to the protons, and the electron clouds are negatively charged due to the electrons. And so what this is trying to state is that we have an attraction between the nucleus of one atom with the electrons of the neighboring atom, and likewise with this side. However, at that same time, there are also repulsions. If you get too close together, the two positive nuclei are going to be repelled by each other because they're both positively charged. And the same thing happens right here with the electrons. But there's this ideal space in between where they are perfectly happy. Okay? And so what happens is that they share this electron cloud. So they become a molecule. Whereas in an ionic interaction, literally, the electron or electrons leave one atom to go to the other. These are sharing. Okay? That being said, although they share electrons, they don't always share them equally. You can imagine, surely some of us have had friends when we were kids growing up, and we would be playing with toys or what have you, and you'd have one friend that was a little bit more stingy with his or her toys than other friends. The same thing happens with the nucleus too. And what happens is that inside these covalent bonds, if they are identical, like here we have fluorine, then they're going to share them perfectly. They both love the electrons just as much as the other atom, so they share them perfectly. However, if we have something like hydrofluoric acid here, HF, it's not shared equally. That fluorine really loves electrons more than the hydrogen does. And so its electron cloud looks considerably different. So if we just look at the electron cloud, what they've done the hypercolor here, is there's more of the electrons located on the fluorine side of the molecule. When with F2, the electron cloud is shared evenly. Okay? Since fluorine pulls harder on the electrons than hydrogens, and it's this unequal pulling, the fluorine end of the molecule is going to have more electron density around it than the hydrogen end. Okay, so it's going to be slightly more negatively charged. It's not really negative charge, but it's going to be slightly more negatively charged than the hydrogen end. A lot of times what they do is they'll say that this one is slightly more negative. That's a lowercase delta, and this one's slightly more positive end. Another way that they like to show it is they draw an arrow to show the direction that the electron density is being pulled, and the end that's more positive, they make it a little plus sign. This is called a polar covalent bond, because in a polar covalent bond, the electron density is not shared evenly. Okay? And so this compound would be a polar compound. So we have to have some way of determining or defining like which atom loves the electrons more than the other atom. And that term comes down to, it's called electronegativity. Right? So electronegativity is literally the ability of atoms to attract electrons to itself. And if you notice here on the periodic table, this one is measured in something called a debye, and the fluorine is the most electronegative atom out there. It has 4 debyes, and it's the most electronegative. And in general, you can see the closer that you get to fluorine, the more electronegative it is. So typically, what you would see is that as you go up the column of the periodic table, it increases, and as you go from left to right, it increases. And so a lot of times I like to draw it as this diagonal. And in class, I would actually be looking for you, if I didn't give you the actual values for the electronegativity, I would just be looking for the logic behind it and how close it is to fluorine. Fluorine is by far the most electronegative, and oxygen is second. Okay, so fluorine is first, oxygen is second in electronegativity. The one exception to this is hydrogen, and hydrogen is approximately equal to carbon. Okay, so fluorine is the most electronegative, followed closely by oxygen. So to reiterate this, as you look along the periodic table, electronegativity tends to increase as you go from left to right, and then as you increase as you go from bottom to the top of a column. So, when 2 atoms share the electrons unequally, and there's a disproportionate pull of the electron cloud towards one atom, you're going to have a slightly positive charge on one end and a slightly negative charge on the other end. And it's called a dipole. Okay? So it's called a dipole. It's really important. And another way that they like to show that, as I mentioned before, rather than saying Q plus and Q minus, because it's not a full charge, is it's a slightly positive charge and a slightly negative charge. They use the small delta sign, or, like in physics, they'll use a vector, which is just an arrow, it shows you the magnitude, and on the end that's more positive, it puts a little plus sign like that. That's to show a dipole, or it's a dipole bond, a polar bond. This is a dipole moment, which is measured in the symbol mu, and it's actually separated by a distance of r. Okay, I would never ask you to calculate the mathematical size of the dipole moment. I want you just to explain like which one is more polar and which is less polar. So for example, let me give you an example of that. We've been talking about HF, and then let's look at water, H2O. Which one of these is going to have a larger polar bond? They're both polar molecules, because as we mentioned before, both fluorine and oxygen are electronegative. They have a high electronegativity, and of course the hydrogen is the same in both hydrofluoric acid and in water. However, that being said, fluorine is even more electronegative than oxygen. So that means that the dipole moment in HF is going to be bigger than the dipole moment in water. So this dipole moment is going to be larger than this dipole moment. So we would say that HF is more polar and water is less polar. So this one's more, this one's less. And once again, it's measured in debyes. Okay, These are just some of the examples. You can see here where as you go down the periodic table, we have the different acids. And if you remember from chapter 2, hydrochloric, hydrobromic, and hydroiodic are strong acids. Hydrofluoric is not. You can see that the bond length increases as you go down the periodic table, and that's because the electronegativity difference decreases. And so the dipole moment decreases as we go down the periodic table. And they show that in these hypercolors here. I just wanted to review, hopefully in section 1 of the chapter 8, I told you that you should go back to chapter 2, review how to name the ionic compounds like sodium chloride and potassium fluoride and things like that. But I wanted to review the molecular, the covalent compounds, because those we have to use the prefixes like mono, di, tri, tetra, so on and so forth. And I want you to know, once again, just like I did before, you have to know 1 to 10. Now you use, the way that you name these is you put the less electronegative atom first, because these are between two nonmetals, and then you put the next, the more electronegative atom second. Okay, now the hydrofluoric acid is different, and like the polyatomic anions themselves, like nitrate, is a little different. But let's just do some examples. And remember, you have to use a prefix. However, if the first atom is 1, we don't say mono. We only say the mono if it's on the second. And I'll show you what I mean. So let's just do some examples. Let's see. Let's compare these two. These are both molecular compounds, and they are both covalent, and they both contain dipole moments because oxygen is more electronegative than carbon. So if we name this first one, we would say carbon because it's a less electronegative, and then it's going to be oxide, because remember these end in IDE typically, but it's carbon monoxide versus carbon dioxide. Okay, let's do another one. Give you a moment. This is P2O10, and I know it's that way because once again we have phosphorus is less electronegative than oxygen. So when we write out the molecular formula for it, we put the phosphorus first, and also when we name it, we name the phosphorus first. But this time we actually have 2 phosphoruses. So it's going to be di-phosphorus. And 10 is deca. But since oxygen also starts with a vowel, they usually drop the A, and so it's decoxide. Let's do one more. So this is CCl4. Once again, carbon comes first because it's less electronegative than chlorine. And so we wouldn't say monocarbon. We would just say carbon. But now 4 is tetra. And then we wouldn't say chlorine. We drop the INE and we say chloride. So it's carbon tetrachloride. Hopefully this has helped refresh your mind and your memory, I should say, in how to name these covalent molecules. I'll see you in class.